The nature of problem solving. As with most of the other topics covered in this book, an extensive amount of theorizing and research on problem solving has been conducted over the years. We will focus our discussion on the types of problems that students are typically required to deal with, the cognitive processes that play a central role in problem solving, and various approaches to teaching problem solving in the classroom. Let's begin by asking what we mean by the term problem and problem solving. Most, if not all, psychologists would agree that a problem is said to exist when one has a goal and has not yet identified a means for reaching that goal. Problem solving, then, is the identification and application of knowledge and skills that result in goal attainment. Although this definition encompasses a wide range of problem types, we will focus on three types that students frequently encounter both in and out of school. Three common problem types. In the first category are the well-structured problems of mathematics and science. The type of problems that students from kindergarten through middle school are typically required to solve. Well-structured problems are clearly formulated, can be solved by recall and application of a specific procedure called an algorithm, and result in a solution that can be evaluated against a well-known, agreed-on standard. For example, 5 plus 8 through 732 minus 485. 3 plus 3x, 8 plus 3x is equal to 40, take away 5x. What constitutes a problem to be solved varies with the age and experience of the learner and the nature of the problem itself. The second of the mathematical examples is likely to be a genuine problem for some first or second graders who are used to seeing subtraction exercises arrayed vertically, minuend on top, subtrahend beneath, horizontal line under the subtrahend. Fifth graders, however, who have had experience with arithmetic assignments in a variety of formats, would be able to retrieve and use the correct algorithm automatically. Because the fifth graders know the means to reach their goal, they do not face a problem-solving task according to our definition, but just a type of exercise or practice. In the second category are the ill-structured problems often encountered in everyday life and in disciplines such as economics or psychology. Ill-structured problems are more complex, provide few cues pointing to solution procedures, and have less definite criteria for determining when the problem has been solved. Examples of ill-structured problems are how to identify and reward good teachers, how to improve access to public buildings and facilities for persons with physical disabilities, and how to increase voter turnout for elections. The third category includes problems that are also ill-structured but that differ from the examples just mentioned in two respects. First, these problems tend to divide people into opposing camps because of the emotions they arouse. Second, the primary goal, at least initially, is not to determine a course of action, but to identify the most reasonable position. These problems are often referred to as issues. Examples of issues are capital punishment, gun control, and non-denominational prayer in classrooms. High school students typically have more opportunities than younger students to deal with ill-structured problems and issues of the type cited above. That does not mean, however, that younger students have no opportunities to deal with ill-structured problems or issues. Consider self-regulated learning, discussed in the preceding chapter. Goal orientation plays a role in the development of self-regulated learning and self-efficacy. Performance goals provide clear, easily specified outcomes. They are similar to well-structured problems. Learning goals, however, are more similar to ill-structured problems or issues. Suppose you have young students who desire to become politicians or firefighters. They will see value in establishing goals that will help them learn the knowledge and skills they need to become politicians or firefighters. Generating personally valued goals can bring opportunities for younger students to solve ill-structured problems. Helping students become good problem solvers. Despite the differences that exist among well-structured problems, ill-structured problems and issues Recent theory and research suggests that good problem solvers employ the same general approach when solving one or another of these problem types. This approach consists of 5 steps or processes. Realize that a problem exists. Understand the nature of the problem. Compile relevant information. Formulate and carry out a solution. Evaluate the solution. Well-structured problems may call only for the implementation of steps 2, 4, and 5, but the other 2 problem types require all 5 steps. We will discuss each of these steps in the next few pages, along with some specific techniques that you can use to help your students become good problem solvers. Step 1. Realize that a problem exists. Most people assume that if a problem is worth solving, they won't have to seek it out. It will make itself known. Like most other assumptions, this one is only partly true. Well-structured problems are often thrust on us by teachers in the form of in-class exercises or homework, or by supervisors at work. Ill-structured problems and issues, however, often remain hidden from most people. It is a characteristic of good problem solvers that they are more sensitive to the existence of problems than most of their peers. The keys to problem recognition, or problem finding as it is sometimes called, are curiosity and dissatisfaction. You need to question why a rule, procedure, or product is the way it is, or to feel frustrated or irritated because something does not work as well as it might. The organization known as Mothers Against Drunk Drivers, for example, was begun by a woman who, because her daughter had been killed in a traffic accident by a drunk driver, was dissatisfied with current ineffective laws. This organization has been instrumental in getting state legislatures to pass laws against drunk driving that mandate more severe penalties. Problem finding does not come readily to most people, possibly because schools emphasize solving well-structured problems, and probably because most people have a natural tendency to assume that things work as well as they can. Like any other cognitive process, however, problem recognition can improve with instruction and practice. Students can be sensitized in a number of ways to the absence or flaws and shortcomings of products, procedures, rules, or whatever else. We will make some specific suggestions about improving problem recognition and the other problem-solving processes a little bit later in suggestions for teaching problem-solving techniques. Step 2, understand the nature of the problem. The second step in the problem-solving process is perhaps the most critical. The problem solver has to construct an optimal representation or understanding of the nature of a problem or issue. The preceding sentence stresses the word optimal for 2 reasons. First, most problems can be expressed in a number of ways. Written problems, for example, can be recast as pictures, equations, graphs, charts, or diagrams. Second, because the way we represent the problem determines the amount and type of solution-relevant information we recall from long-term memory, some representations are better than others. For obvious reasons, problem-solving researchers often refer to this process as problem representation or problem framing. To achieve an optimal understanding of a problem, an individual needs 2 things: a high degree of knowledge of the subject matter, facts, concepts, and principles, on which the problem is based, and familiarity with particular types of problem. This background will allow the person to recognize important elements, words, phrases, and numbers in the problem statement and patterns of relationships among the problem elements. This recognition will activate one or more solution-relevant schemes from long-term memory. It is this level of knowledge of subject matter and problem types that distinguishes the high-quality problem representations of the expert problem solver from the low-quality representations of the novice. Experts typically represent problems in terms of one or more basic patterns or underlying principles, whereas novices focus on limited or superficial surface features of the problems. To give you a clearer idea of the nature and power of an optimal problem representation, consider the following situation. When novices are given a set of physics problems to solve, they sort them into categories on the basis of some noticeable feature. For example, they group together all problems that involve the use of an inclined plane, or all the ones that involve the use of pulleys. Then novices search their memories for previously learned information. The drawback to this approach is that although 2 or 3 problems may involve the use of an inclined plane, their solutions may depend on the application of different laws of physics. Experts, in contrast, draw on their extensive and well-organized knowledge base to represent groups of problems according to a common underlying principle, such as conservation of energy or Newton's third law. An important aspect of the problem-solving process is the ability to activate relevant schemes, organized collections of facts, concepts, principles, and procedures from long-term memory when they are needed. The more relevant and powerful the activated scheme is, the more likely it is that an effective problem solution will be achieved. But as many observers of education have pointed out, acquiring this ability is often easier said than done. John Bransford argues that standard educational practices produce knowledge that is inert. As mentioned earlier in the chapter, inert knowledge can be accessed only under conditions that closely mimic the original learning context. Richard Feynman, a Nobel Prize-winning physicist, made the same observation in describing how his classmates at the Massachusetts Institute of Technology failed to recognize the application of a previously learned mathematical formula. They didn't put 2 and 2 together. They didn't even know what they knew. I don't know what's the matter with people. They don't learn by understanding. They learn by some other way, by rote or something. Their knowledge is so fragile. To overcome this limitation of inert and fragile knowledge, teachers need to present subject matter in a highly organized fashion, and students need to learn more about the various conditions under which their knowledge applies. Compile relevant information. For well-structured problems that are relatively simple and familiar, such as arithmetic drill problems, this step in the problem-solving process occurs simultaneously with problem representation. In the process of defining a problem, we very quickly and easily recall from long-term memory all the information needed to achieve a solution. As problems and issues become more complex, however, we run into 2 difficulties. The amount of information relevant to the solution becomes too great to keep track of mentally, and there is an increasing chance that we may not process all the relevant information. As a result, we are forced to compile what we know in the form of lists, tables, pictures, graphs, and diagrams, and so on, and to seek additional information from other sources. The key to using oneself as an information source is the ability to accurately retrieve from long-term memory information that will aid in the solution of the problem. We need to think back over what we have learned in some somewhat similar situations, make a list of some other form of representation of those ideas, and make a judgment as to how helpful that knowledge might be. Techniques for ensuring accurate and reliable recall were discussed in Chapter 8 on information processing theory. In addition to relying on our own knowledge and experience to solve problems, we can draw on the knowledge and experience of friends, colleagues, and experts. The main purpose of soliciting the views of others about solutions to problems and positions on issues is to identify the reasons and evidence those people offer in support of their positions. This skill of asking questions and analyzing responses is quite useful in debates and classroom discussions of controversial issues. Formulate and carry out a solution. Step 4. When you think you understand the nature of the problem or issue and possess sufficient relevant information, you are ready to attempt a solution. The first step is to consider which of several alternative approaches is likely to be most effective. The literature on problem solving mentions quite a few solution strategies. Because these solution strategies are very general, they can apply to different kinds of problems in different content areas and offer only a general approach to solving a problem. They are referred to as heuristics. We will discuss 7 heuristics that we think are particularly useful. Study worked examples. This approach may strike you as so obvious that it hardly merits attention. But it is worth mentioning for 2 reasons. First, obvious solution strategies are the ones that are most often overlooked. Second, it is a very effective solution strategy. The beneficial effect is thought to be due to the learner's acquisition of a general problem schema. To get the most out of this heuristic, use multiple examples in different formats for each problem type and encourage learners to explain to themselves the problem-solving strategy illustrated by the examples. Work on a simpler version of the problem. This is another common and very effective approach. Geometry offers a particularly clear example of working on a simpler problem. If you're having difficulty solving a problem of solid geometry, which involves 3 dimensions, work out a similar problem in plane geometry, 2 dimensions, and then apply the solution to the 3-dimensional example. Architects and engineers employ this approach when they construct scaled-down models of bridges, buildings, experimental aircraft, and the like. Scientists do the same thing by creating laboratory simulations of real-world phenomena. Break the problem into parts. The key to this approach is to make sure you break the problem into manageable parts. Whether you can do this will depend largely on how much subject matter knowledge you have. The more you know about the domain from which the problem comes, the easier it is to know how to break a problem into logical, easy-to-handle parts. At least 2 benefits result from breaking a problem into parts. It reduces the amount of information you have to keep in short-term memory to a manageable level, and the method used to solve one part of the problem can often be used to solve another part. Bransford and Stein use the following example to illustrate how this approach works. Problem: what day follows the day before yesterday if 2 days from now will be Sunday? What is today if 2 days from now will be Sunday? Friday. If today is Friday, what is the day before yesterday? Wednesday. What day follows Wednesday? Thursday. Work backward. This is a particularly good solution strategy to use whenever the goal is clear, but the beginning state is not. Bransford and Stein offer the following example. Suppose you arrange to meet someone at a restaurant across town at noon. When should you leave your office to be sure of arriving on time? By working backward from your destination and arrival time, it takes about 10 minutes to find a parking spot and walk to the restaurant. It takes about 30 minutes to drive to the area where you would park. It takes about so many minutes to walk from your office to your car. You would more quickly and easily determine when you leave the office, about 11:15, than if you had worked the problem forward. Backward fading. Students vary in how much they know about the subject matter on which the problems are based, and students with more prior knowledge do better on problem-solving tests when they are given problem-solving instruction and practice than when they are given worked examples to study. For these reasons, a good procedure to use with all students is something called backward fading. Backward fading is basically a combination of studying worked examples, working backward, and practicing solving problems. First, a completely worked out example, such as one that requires 3 steps to complete, is provided. Then a similar problem is presented with only the first 2 steps worked out. The last step has to be completed by the learner. The third problem provides the solution to the first step and requires the learner to determine the solution for steps 2 and 3. Finally, the fourth problem requires the learner to solve all 3 steps. Compared with peers who saw ordinary worked examples and practiced solving problems, a group of college students who were exposed to the backward fading procedure scored significantly better on problems than that were both similar to and different from the practiced problems. Solve an analogous problem. If you're having difficulty solving a problem, possibly because your knowledge of the subject matter is incomplete, it may be useful to think of a similar problem about a subject in which you are more knowledgeable. Solve the analogous problem, and then use the same method to solve the first problem. In essence, this is a way of making the unfamiliar familiar. Although solving analogous problems is a very powerful solution strategy, it can be difficult to employ, especially for novices. In our previous discussion of understanding the problem, we made the point that novices represent problems on the basis of superficial features, whereas experts operate from knowledge of underlying concepts and principles. The same is true of analogies. Most of us know that DNA is somehow related to the image of a twisted ladder, called the double helix, but there is much more to mapping the human genome than visualizing a twisted ladder. Novices are more likely than experts to use superficial analogies. Analogous problems are discussed in the upcoming suggestions for teaching and in the resources for further investigation at the end of the chapter. Create an external representation of the problem. This heuristic is doubly useful because it also aids in problem framing. Many problems can be represented as pictures, equations, graphs, flowcharts, and the like. The figures in the next suggestions for teaching section illustrate how a pictorial or symbolic form of representation can help one both understand and solve the problem. Step 5. Evaluate the solution. The last step in the problem-solving process is to evaluate the adequacy of the solution. For relatively simple, well-structured problems in which the emphasis is on producing a correct response, 2 levels of evaluation are available. The problem solver can ask whether, given the problem statement, the answer makes sense. For example, if the problem reads 75 times 5 equals, and the response is 80, a little voice inside the problem solver's head should say that the answer cannot possibly be right. This signal should prompt a reevaluation of the way the problem was represented and the solution procedure that was used. For example, I misread the time sign as a plus sign, and I added when I should have multiplied. The problem solver can use an alternative algorithm to check the accuracy of the solution. This is necessary because an error in carrying out an algorithm can produce an incorrect response that is still in the ballpark. For example, a common error in multiple column subtraction problems is to subtract a smaller digit from a larger one, regardless of whether the smaller number is in the minuend, the top row, or the subtrahend, the bottom row. As in 522, take away 418, and because of this answer is off by only 12 units, it looks right. The flaw can be discovered, however, by adding the answer to the subtrahend to produce the minuend. The evaluation of solutions to ill-structured problems is still likely to be more complicated and time-consuming for at least 2 reasons. First, the evaluation should occur both before and after the solution is implemented. Although many flaws and omissions can be identified and corrected beforehand, some will slip through. There is much to be learned by observing the effects of our solutions. Second, because these ill-structured problems are complex, often involving a dozen or more variables, some sort of systematic framework should guide the evaluation. Vincent Ruggiero suggests a 4-step procedure. Ask and answer a set of basic questions. Imagine, for example, that you have proposed a classroom incentive system, a token economy perhaps, to enhance student motivation. You might ask such questions as, how will this program be implemented? By whom? When? And where? With what materials? How will the materials be obtained? Identify imperfections and complications. Is this idea, for example, safe, convenient, efficient, economical, and compatible with existing policies and practices? Anticipate possible negative reactions from other people. For instance, might parents or the school principal object? Devise improvements. The next section contains guidelines and examples that will help you improve the problem-solving skills of your students. Pause and reflect. Critics of American education argue that students are poor problem solvers because they receive little systematic instruction in problem solving processes. How would you rate the instruction you received in problem solving? In terms of the 5 steps discussed on the preceding pages, which ones were you taught? What can you use to ensure that your students become good problem solvers?